Here we go. All right, guys, so today what we're going to do is we are finally going to set the stage for what you need to know to go to lab. But, guys, this is actually the way that this is going to go. In the next 30 minutes, I am going to teach you everything that you need to know about calorimetry to do this on the test. Because, guys, in the AP curriculum, they dumb this down. So, guys, everything that we're going to learn in the next 30 minutes, that's the level at which you need to know it on the AP test. Then, guys, in third period, we're going to actually clean it up and we're going to do it right. So this is going to be an interesting conversation. We're going to start with what you need to know for the test, and then after we take a break, we're going to come back and make it even better. You're going to love it. So, guys, what we need to do to get started is this. Please just trust me, don't write this down until I tell you. So, guys, this is where we're at right now. Don't write it down. Thermochemical equations, right? And we talked about these ideas that they are for the moles written. So 1 mole of methane Bunsen burner gas, when it burns, gives off about 900 kilojoules of energy. We know that it gives it off because this number is negative. And if we were to double this, we'd double that, and so on. Yes? Guys, today what we're going to do is we're going to ask the question, where do these numbers come from? Please don't write this down. So guys, if we've got a generic reaction, and if we know the delta H for the reaction, where does the value come from? And the answer is this. We get enthalpy change data. We get enthalpy change data from 2 places. One is empirically, and what does empirical mean? Measured in lab, and we call that calorimetry. Guess what we're doing today? Calorimetry. But guys, there's another way to do this, and this is through Hess's law. Where'd my bottle go? Can you tell I'm searching? Oh, there it is. Did you guys not know about what happens inside there? Oh. I think that they should let me teach a class called Let's Sit Around and Think About Science. Wouldn't that be fun? I know, it'd be so fun. Yeah, just like, hey, why does this get cold? And then we can talk. I think what they really should do is they should teach a class called Hang Out with Ellingford. Could you imagine? You'd say that again? Oh yeah, and you'd probably gain a lot of weight, and you could learn words that nobody understands. And you could, oh my gosh, it would be unbelievable. Yeah, and you'd learn magic. Yeah. Oh, that would be trouble. Yeah, I don't know if I could do both of them at once. My head just isn't that pliable anymore. All right, so guys, there's another way to do this, which is called Hess's law. Not on Friday, on Tuesday, because I'm going to be gone on Friday, and we'll talk more later. Guys, this can be done through manipulation, and this can be done through computation. Guys, up until about 5 years ago, I used to teach these things separately. But you guys understand this, right? While I'm teaching, I'm always learning stuff. It's like that, and sometimes you just have these moments where you're like, no way, that's really cool. And what I found out about 5 years ago is that these are actually the same, and I didn't even know it. I've been teaching it for years, and as I was going through this, because you guys understand I don't lesson plan, right? I don't plan, I just get up here and let's see how it goes. And so guys, as I was teaching this about 5 years ago, I was like, wait a minute. Those are the same. And it was actually really cool. So now that's how I teach it. And you'll see. So guys, today we're going to do calorimetry. On Tuesday, we're going to go both forms of Hess's law. And then we're going to go into chapter 19 from there. You guys good? All right. So guys, foundational stuff. Grab your AP equation sheets. Hey! Who needs one? You guys good? Don't be shy. You need one. Let me give you one. Come on. Who Who else? Make me feel useful. John, I'm giving you one too. Come on. There you go. Cheat sheets for all my friends. All right. A couple of years ago, I had this group of students that, and don't you dare do this. I had this group of students that thought it would be funny to start hiding these sheets around my room. Don't you dare. One of those kids has actually never been found. He just disappeared. May or may have not been my doing, but he just disappeared. They're still not sure where he is. Never mind. Okay. Oh, shoot, it is. All right. Okay, so guys. Yeah, I did. Yeah, that's what that means. Okay, so guys, this is the foundational math. So when we talk about heat, the transfer of energy through hot things, making hot things cold. Guys, there's two ways and you got to write this down, word for stinking word. This is very, very, how do I say this? The verbiage matters. I don't even know if that's a good way to say this. But guys, it's not just good enough to be close enough. You've got to get these words right. So guys, when we talk about heat capacity is the amount of energy needed to raise a system's temperature 1 degree Celsius. And guys, if you read this, your ears are probably itching a little bit. Because you're going, wait, didn't I write down something like this before? The calorie, but that's not this. And so in a calorie, the system is water. Go ahead.
So if you in that system, you have like
Guess what we're going to do in third period? That's exactly the problem. So guys, Jonah is hot on the tail of this. What if you have a system, or worse yet, a surroundings that has multiple heat capacities? The answer is brilliant. We'll talk third period. Okay. But guys, the idea is this. Heat capacity is the amount of energy needed to raise a system temperature 1 degree Celsius. Now guys, pause. You understand that this kind of looks like the calorie. There's two ways that it's different than the calorie. One is it's not water. What's the other? Good. Dang, Michael. Yes. It is not mass dependent. It is a system, and that system could be huge or teeny, which Jonah sort of gets us started on your idea. Guys, it doesn't matter how big it is. There's no mass. Therefore, I turned off my board. Guys, therefore, we have an equation that doesn't include mass. So here it goes. Guys, heat capacity is abbreviated H sub C. Wait, heat is enthalpy. Yes, but H is enthalpy, but that's not heat. But what is it? Shouldn't it be? Guys, this is heat capacity. It is denoted H for heat, which is really Q, and H is enthalpy, but we're not doing work, so it doesn't matter. And so we denoted H sub C, and this then is the equation. And you may like this better if you write it Q over delta T. Maybe I should turn my board on. So I do. I'll turn it on. Yeah, actually, I have to turn it on. I got to be able to write. All right. There we go. So guys, I would suggest that maybe a better form for this for you is H sub C is equal to Q divided by delta T. So you ready? Imagine that we have a system and we dump 1,000 joules of energy in the system and the temperature goes up 10 degrees. What's H sub C? 1,000 joules, 10 degrees. 100, right? So that would be 100 joules per Celsius degree. So what do we now know? Well, guys, if we know H sub C to be 100 joules per Celsius degree, what if we take that same system, dump some energy into it, and the temperature goes up 5 degrees? 500 joules, get it? So guys, the idea, and this is part of calorimetry, is we are going to determine the heat capacities of systems, and once we've established that, we can then track the temperature of the system and figure out how much energy went in or out. Huh? Oh, just like science. Now guys, this. Mila, don't. That's me laughing at you. Guys, the units are joules per Celsius degree. Now, guys, this specific heat. And guys, the really bad part is sometimes they call it specific heat capacity. Let's don't. So what is specific heat? Guys, the definition for specific heat is this. The amount of energy needed to raise a gram of a substance's temperature, 1 degree Celsius. Write that down too. Bless you. Next thing we were going to talk about. Guys, if you've got what I like to call Elizabeth smarts, then you're on that same idea. Guys, the specific heat of water is 1. The specific heat of water is 1. But we represent this with a little c. So calories are like joules. They're a unit of energy. Oh, because calories is big C. And we're going to look at the AP equation sheet in just a minute. Maybe. We'll talk. It's funny, no one's ever brought that up. You're going to find that you're going to know these equations so well in context that you'll never be confused. You'll be good, yeah.
So Celsius is the small circle driver. Why is the 1 Celsius different from the others? Yeah, does that matter?
Yeah, good question. So, not to me, and not to the AP graders, but technically yes. And so when we are talking about specific measurements, it is 1 degree Celsius. But if we're talking about generic units for something, it is Celsius degrees. So in theory, it does matter. It gets even worse when we talk about Kelvin, because Kelvin are not degrees. And we'll talk more about that later. But in theory, it matters, and here it doesn't. And on the AP test, it doesn't. So you'll have college professors that'll nail you for it, but you're fine. All right. So guys, this then leads us to an equation. Q is equal to what we lovingly like to call MCAT. So guys, what is M? Give me an M. Mass. What is delta T? Change in temperature. What's C? Specific heat. So the amount of energy Q that is added or removed from a system is equal to its mass times its specific heat times its change in temperature. Now, I hope this is in here. It's not, but we should talk about this. So guys, coming back to Elizabeth's idea, 1 gram, right? So specific heat is specific to a gram of a substance. If that is water, it then becomes this. So guys, the specific heat of water is 1... let me clean up my mess, sorry. Guys, the specific heat of water is 1 calorie per gram. No, sorry, that goes on the bottom. 1 calorie per gram per Celsius degree. That is the specific heat of water. 1 calorie per gram per Celsius degree. If that doesn't make sense, do this. Take this equation and solve it for C. So C is Q divided by M delta T. So Q is energy, M is mass, delta T is temperature change. And so our units are calories per gram per Celsius degree if it's water. But we don't talk about calories. What do we use? Joules. And so guys, the specific heat of water is 4.184 joules per gram per Celsius degree. Just a second. That's the one you need to know. So now, Jared, can I table your thought for just a minute? Guys, go to the AP equation sheet and let's make sure we're okay. So guys, go to the thermo page. Dun, dun, dun. Page 4. Bless you. So guys, have you ever thought about this? That all of these equations that you see in front of you on these 2 equation pages, by April, you're going to know every single one of these? Okay. So look down at the bottom of page 4, thermochemistry and electrochem. We don't put those together, but they do. See the very top one, Q is equal to M, little m cap? So let's look. Off to the right are what the equation, what the variables mean. Q is heat, M is mass, C is the specific heat capacity. Uh-oh. Guys, it doesn't say specific heat, it says specific heat capacity. We're not going to call it that. We're just going to call it specific heat because then it's less confusing. But if you want to next to this put parenthetically capacity, that's what they will call it on the AP test, or on the AP equation sheet, but you can just call it specific heat and that's fine. John, what did they call it in physics? Did they call it specific heat or heat capacity? Never mind. Moving. Because heaven knows heat transfer is such an unimportant topic in physics. Okay, so, and then guys, moving along, there's your T is temperature, you know delta, and you're out the door. What's missing? What is missing from this paper compared to what's on the board? Oh, dear goodness, please. Look at the board. Then look at the paper. What is on the board that is not on the paper? Heat capacity. Guys, here's the deal. For the AP test, this is what you've got to understand and manipulate. In lab, we are going to invite heat capacity into the conversation, and then we can do thinking and science that's better and more interesting, especially given Jonah's question a minute ago. But you don't need to know it for the AP test. So on the AP test, all you got to know is this. We're going to bring this into the conversation in about 20 minutes because it's more interesting and it's better science. Good? All right. So guys, here we go. Go ahead, Mila. Cue. All right. Y'all ready? Please say yes. Hey, coffee cup calorimetry. So guys, understand Utah County, I know this means nothing to you because of the stigmas against coffee, but in the rest of the world, you say coffee cup calorimetry and people go, I know what that is. So guys, when you think coffee cup, think styrofoam cup, okay? So guys, literally in the sciences, they call this coffee cup calorimetry. You could think of it as hot chocolate cup calorimetry. Or if you're really old, do y'all know what postum is? Besides disgusting. Oh yeah, it's horrible. So guys, postum is what people 30 years ago in Utah County drank because even back then hot chocolate was edgy because it had caffeine in it. Postum's nasty, don't touch it. But guys, the bottom line is this. Whether it's hot chocolate or coffee or postum, don't draw it. This is it. Guys, this is coffee cup calorimetry. This is what you are going to do in lab on Tuesday. Yeah, but we're going to draw it in just a minute. But guys, let me introduce you to the parts and the bits. So guys, first of all this, we are not doing work. How do we know we're not doing work? No. Constant pressure. You guys, constant pressure. Therefore, work is not being done. So if work is not being done, how does energy get in and out of this thing? Heat. But now, guys, this. When we do coffee cup calorimetry, we need a system and we need a surroundings. And guys, here's what we're going to do. Our system is going to be our reactants becoming products. In the first lab that we're going to do, those are acids reacting with bases. In the second lab that we're going to do, it is going to be salts dissolving into water. Okay? That is our system. So guys, if that is our system, what does it make everything else? The surroundings. But now, guys, we're going to get sneaky, and Jonah, you're going to see that this is starting to edge towards your question. Guys, this is the magic of this process. This is a nesting of styrofoam cups. So, guys, if you've ever bought a hot drink from a restaurant or a shop or whatever, either they will double up the cups or they'll put a sleeve around it. Why? You don't burn yourself, right? So what do those cups or that sleeve do to heat? Insulated. So guys, here's what we're going to do. We understand that our surroundings is everything else, right? But guys, that is unmanageable. Again, it is unmanageable for our surroundings to be the universe. So this is what we do in coffee cup calorimetry. We say that this and the lid are an impenetrable barrier. And heat cannot get through the styrofoam. It's insulated from the rest of the universe. And if that's the case, and if this is our system, what is now our surroundings? And guys, the answer is the guts of the coffee cup calorimeter. So this becomes a boundary. And if this is a boundary, then everything inside of here is going to be our surroundings, our little mini universe. So what's in there? Well, guys, the first thing that's in there is water. In order to do coffee cup calorimetry, it has got to be aqueous reactions. Pause and think about that from the last unit. Aqueous reactions, right? That's water. But guys, water is not part of the system, it's part of the surroundings. Then guys, another part of the surroundings is a stirry thing. In real constant pressure calorimeters, you can buy these, they're really expensive. It's actually a little impeller that's driven by a motor. For us, it's going to be a thing of wire, and you're just going to move it up and down to stir. Then guys, in addition to that, we've got a thermometer. That is also part of the surroundings that we can measure. You get the idea? Now guys, this. On the AP test, this goes away and this goes away. We pretend that there is not a stirry thing, and we pretend that there is not a thermometer. So minus the stirry thing and minus the thermometer, what's the only thing left? Aha! The water. And so guys, the chemistry now goes like this. This is our system. And guys, let's say that whatever that system is, let's say it's exothermic. So what's the value for delta H? Negative. Energy out, right? So guys, say that that sample, that system is a reaction and it's releasing energy. Now guys, where does the energy go? Into the water. We're going to pretend like the stir and the thermometer aren't there. So all the energy in the form of heat goes out of the system and into the water, and that's it. On the AP test, you'll see it written like this. Assume that all the energy lost by the reaction is absorbed by the water. Get it? Okay. But guys, what is all that heat going to do to the water? Make it heat up. Make its temperature go up. And guys, here's what we can do. We can measure the mass of the water. Then we can measure the temperature of the water initially before the reaction started. Then we can measure the temperature of the water finally. If this is exothermic, what will happen to the temperature of the water? It will go up. And then look at what we can do. Q is equal to MCAT. This is the mass of the water. This is the temperature change of the water, and we know C, 4.18 joules per gram per Celsius degree. What we can then do is we can calculate the amount of energy gained by the water. But guess what that's equal to? The amount of energy lost by the system. First law of thermodynamics, right? And that's what we're going to do. We are going to measure the mass of the water. We're going to measure the temperature change of the water. By knowing C, we can figure out the amount of energy gained by the water, which is equal to the amount of energy lost by the reaction. Does that make sense? But guys, understand this idea that Q lost by the reaction is equal to Q gained by the water only works if one thing is true. What's that? It's perfectly insulated. So now guys, let's talk. If you've ever bought a hot drink, and if it comes in a, doubled up cup or a sleeve, you go to drink that thing and you're like, hey, this isn't burning my hand, but you go to drink and you're like, ooh, too hot. And then you set it down and you come back 2 hours later and you drink the drink, and what's it like? Room temperature. Why? Because the cup is actually not a good insulator. Guys, that's true here too. These cups are actually not perfect insulators. The question is, how do we deal with that? The answer is coming after break. See what we did right there? After the break. Keeps them coming back. Keeps them coming back. So guys, I'm going to pause. I'm going to start recording again. And we're going to go here. Would anybody like to laugh at me in Mila's place? Thank you. I know, it's really not. No, Mila's annoying in her own special little way. And I love her. I can say that, though, because we're friends. Okay, so, guys, let's review, because this is about to get wicked interesting. You ready? So here's where we are. Coffee cup calorimetry. Aqueous chemistry only. Our system is the thing doing chemistry. At first, those will be acid and base molecules reacting together to form salts and water. Then, guys, you're going to come back and you're going to do a whole nother lab where your system will be salts. And those salts will dissolve in water. Technically a physical process, not chemical. But it still releases or takes in energy. We're going to talk about endothermic salts. We're going to talk about exothermic salts. And then you guys are going to design and carry out your very own lab. Now, with that said, we understand our sample, but we also understand that we've got an insulated container that is a barrier that limits our understanding of the universe down to the surroundings that are inside the cup. Those include a thermometer, a stirry dude, and water. Again, on the AP test, we will disregard the stirry thing and the thermometer, and that leaves us with water. And when we're left with water, then guys, this equation is sufficient because the energy, in this case, that is lost, exothermic, the energy that's lost by the reaction is equal to the energy gained by the water. Can I get an amen? Okay. Guys, this is what you need to know for the AP test, but we can do it better. So if you would like the homework assignment, none of which will be due, it's this. So guys, 49A and B, 50, 51, 55, 63, 65, 67, 69A and B, 73A and B. I'll show that to you again on Tuesday. The thing that the part of this homework that will be due on Tuesday is the second part, summarizing chapter 19. But you're going to have time with a sub on Friday to do that. So it too will not be homework. Okay? Bring your books. And guys, also let's just talk about Friday. So Friday is an assembly day because it's homecoming. And so guys, we're going to have short class periods on Friday. John, I'll try to get the schedule before you leave. So guys, my sub plans for second and third period on Friday are simply going to be get out of their way. They got stuff to do. So guys, the stuff that you're going to be working on Friday include the following things. Jared, don't get too pulled away. It involves the following things. We have a lab to write up, right? We have that quantitative analysis lab that needs to be written up, and the conclusion questions need to be done, okay? In addition to that, you have chapter 19 to summarize. In addition to that, you will have the pre-lab for the next lab that we're doing, and I'll give you that in a minute. So guys, you got plenty to do on Friday, including chapter 19 summary, wrapping up the quant lab, and pre-labbing the calorimetry lab. Okay, those will be your things for Friday. And you'll have all of that in your possession, and we'll go from there. You guys okay? Okay. All right, guys, here we go. You already have a sheet of paper going. Is it important? Do you guys have like a section in your lab notebook where you write down ideas? Is that a thing? Let's do this. It could be. I've got ideas. Maybe I should write them down. So guys, this is what we're going to do. We are now going to take our coffee cup calorimeter and we are going to push it to make it better. I would strongly encourage you to get this on paper. If that's a continuation of your notes, that's great. You're going to need a whole sheet of paper. If you would like to make that a new sheet, great. But guys, you are going to send me emails. You are going to write poetry. You are going to name your children after me. When you get to college and you find out that it's really this straightforward when you try to figure this out in college from a professor or a TA that actually doesn't like you. So, you guys ready? Here we go. Calorimetry. Guys, sometimes people get really confused here because they see, why doesn't that work? That's a no-brainer because I quit. Okay. So guys, wow, this is really freaking out. So guys, sometimes people get confused because they see this and they automatically think it's a It's not a beaker, it's a calorimeter. You can see the difference. Obvious. Okay, good. Well, you would think, but I don't know what a trapezoid is, so we're just going to leave that alone. Okay, so guys, draw yourself this, 3 by 2 inches, big, grande, in the middle, not at the top, in the middle. Yeah, not at the top. You want room all around this. Do you need another sheet of paper? All right, then guys, let's turn this into a calorimeter. Do not draw this, but let's be clear. For the calorimeters that we are going to build in lab, we are going to be nesting cups together to get better insulation. But we're just going to draw it as a single wall for simplicity. Then guys, please do this. Please don't draw until I'm done. You are going to put a lid on your calorimeter, but that lid is going to need a penetration through it. In lab, your lid will be a piece of cardboard. And actually, the hole will be right in the middle. Then guys, through that hole, Elizabeth, tell me if this is a trapezoid. Nope, that's an eraser. Not a trapezoid. So, we've got this, and this, and this. Is that a trapezoid? Hey, I made a trapezoid. But this trapezoid is actually a 2-hole stopper. Actually, that's not true. It's a 1-hole stopper. And guys, through this stopper, we are going to pass a thermometer. But in addition to that thermometer, we are also going to pass a piece of nichrome wire. It's nickel chromium wire. Surprisingly, it's steel, but it doesn't react with acids. It's kind of funny that way. It's called nichrome wire. And guys, what you're going to see is at the top of the nichrome wire, there will be a bend. And you will use this as a stirry thingy because it will be looped around your thermometer, and then you will move it up and down the thermometer to stir the reactions. You with me so far? Okay. Now guys, this. Let's catch up. This is really being strange. Can I just stay in black? Is that okay? Yeah. Okay. So guys, let's do this. Let's put our system in there. Again, the first lab, they will be acids and bases. Our second lab, they will be dissolving salts. Now guys, for the sake of this conversation, let's say that our system, or the reactions that are taking place in our system, let's just say that they're exothermic. Now understand, they could be, well, that's not true. The acid and base reactions, those are exothermic. But in lab, your dissolving salt might be endothermic. But let's just say exothermic for now, just because it lets us talk about direction more easily. So now guys, let's do this. What is now missing from our calorimeter? Water. So let's put some water in here. Now, and guys, this we need to keep track of. Draw carefully, and then we're going to catch up with where we were a minute ago. So guys, heat out. Draw you some heat out. But guys, where is that heat going? Into the water. And how can we measure how much heat went out of the reaction? Well, what we do is we measure the mass. We know the heat capacity of water. We measure the change in temperature. We multiply those together, and that gives us the amount of energy lost by the system, gained by the water. So this gets us there. You guys okay? Again, on the AP test, it will say to you, assume that all the heat lost by the system is gained only by the water. And then, guys, at that point, we're good to go. But guys, we know from experience this is not really what's happening. On the AP test, they simplify it to this level. But IRL, there's a whole lot going on. IRW? No, not in real life, real world. In the real world, IRW, real world. Yeah, you get me. Okay, so let's not meet. Okay, so here we go. So guys, what is really going on? Where else is the heat really going? Okay, so let's talk about that. I'm trying to figure out how this is going to fit best on the paper. Let's do this. We also have energy going into the water and then into the room. So let's put that there. And guys, in order for us to really understand what is going on with this reaction, we can't just ignore that. Because we know if we come back 2 hours later, our hot cup of coffee is now room temperature. What happened? Well, guys, the energy leaked through the styrofoam, and that happens. So if we really want to know how much energy this system is losing, we got to account for that. The way that we do it is brilliant. But guys, that's not the end of the story. Where else does the energy go? Into the thermometer. And the stirry dude. And the air. And the stopper. And the lid. And the cup. So guys, a bunch of this energy goes into the calorimeter itself. And we have to be able to account for that as well. So guys, we now have to track all of this down. The vast majority of the energy does in fact go into the water. Jonah was sort of alluding to this a minute ago. Guys, the heat capacity of water is stupid high. It's going to soak up a bunch of energy. So most of the energy goes into the water. But guys, some of the energy goes through the cup and into the room, and some of the energy goes into the parts of the calorimeter. How do we account for that? Well, guys, let's talk about the calorimeter first. So what we want to know, and you're writing this down with me, what we want to know is how much heat went into the calorimeter. But guys, in order to do that, we're going to reframe this a little bit. We're going to do this differently. So what we really want to know is this. This should sort of ring in your ears. Guys, what we want to know is if the temperature of the calorimeter went up this much, how much energy did it absorb? Remember that silly thing that we talked about? I'm going to go to a clean screen to remind you. Remember we talked about this idea, if we dump 1,000 joules of energy into a system and its temperature goes up 10 degrees, what is the heat capacity? 100? Does 100 joules per Celsius degree? So guys, we know that this is 100 joules per Celsius degree. Then, if we take that same system and we dump energy into it, and if its temperature goes up 5 degrees Celsius, how much energy went in? Wouldn't it be nice to know that information about our calorimeter? Because if we know how sensitive our calorimeter is to energy absorption, we can then figure out how much energy it absorbed. Now guys, here's the deal. If you become a calorimetric chemist, you buy a calorimeter that actually is already calibrated, and stamped on the side of it, it says the heat capacity of the calorimeter. But we're making ours out of cardboard and coffee cups. So guess what we get to do? Calibrate it. And this is how. Guys, what you're going to do, hi Mila, try to catch up, but this could be tricky. Really, the best thing to do would be to just pick up here. So, Mila, what we've said is this. We just caught up to where we were. We said that in a calorimeter, energy is lost by the system. It goes into the water. We know how much energy by knowing the mass and the change of temperature for the water. Now, what we've said is this. This isn't really true. Actually, some of the energy goes into the room, and some of the energy goes into the calorimeter, and we're trying to figure that out. So, guys, this is what you're going to do. I'm going to write it on another screen, and then we'll come back and we'll make it into something we can put on the paper. So guys, here's what you're going to do. Don't write this down. This is your calorimeter. And guys, here's what you're going to do. Using easy numbers, you are going to take some mass of 100-degree water. You know that's impossible in Utah because water boils at 96, right? Let's use 100 because it's easy. Then you are going to take the same mass of 20-degree water. Let's say that's room temperature. You ready? If the masses are the same, when you mix the water, what will the temperature be? Give me a number. 60. Because guys, what's happening is the hot water is losing energy to the cold water, and the first law of thermo says that as the hot water loses energy, the cold water gains energy, and the amount lost by the hot is gained by the cold. And they end up in the middle at 60 degrees. Get it? But that's not really what happens. Where does the where does the temperature end up relative to 60? Why? Boom. It ends up below 60 because energy goes into the calorimeter. So guys, make a mental note. We'll talk more next week. This is the first thing you're going to do in lab when you get over there next week, is you're going to calibrate your calorimeter. Now guys, watch. Some of you are going to go over into lab and you're going to add the 100-degree water. And actually, technically, what you're doing is this. You're going to put the 20-degree water in the calorimeter. Then you're going to dump in the 100-degree water and you're going to measure the temperature. Shouldn't be 60. It should be lower than 60. And again, these aren't really the numbers you're using, but you're going to get in there and you're going to measure the temperature and it's going to be 62. If that happens, you have got to hit a board on your lab. Just a minute. Now guys, and this isn't me being heavy and this isn't me being weird, but guys, we learned an important lesson early in the year. Details matter and it's important to stay focused. And a lot of us in here didn't do that, and that last lab went bonkers. So guys, this is a detail that, and I'll remind you on Tuesday, this is a detail you've got to keep track of. If you mix the hot and cold water together and your final temperature is higher than the average, you screwed up and you got to do it over. And if you don't, the entire lab is broken, and I'm not going to let you suck data from other people. You're going to come back and do it on your own time. Okay? That one's important. Jared, go ahead. Yeah, but here's the thing thank you. Let's talk about that. So yeah, couldn't it be higher than the average because this is the uncorrected temperature, right, from your thermometer? So what should we do? We should correct the temperature. But why don't we have to? We're actually not. Closer. What is it that we actually need? We don't need the temperature. We need the change in temperature. And I don't know if you remember learning this from Miss Call last year. It was very early in the year, and we talked about the idea of mass by difference. So instead of weighing sugar, you weigh a beaker, then you weigh the beaker plus the sugar. And if both of those are wrong, you can still get the mass of the beaker because the errors subtract out. You know what I'm saying? Same thing's going on here. We really don't need to know that final temperature. What we need to know is the temperature change. So say that this goes to 58. So What was initially the temperature of the calorimeter? The same as the cold water. So the calorimeter started at the same temperature of the cold water, 20, and it went up to 58. And as a result, that change would be 38 degrees, and that's eventually what we're going to plug into the equation. So now I know you're going, wait a minute, we actually really do need to know that temperature, because in this case, we're not looking for change, we're looking for averages. But what you can do is you can actually go, okay, so this went up to 58. I know that this is 20, and you can do that subtraction just in your head. And if that subtraction results in a number that's smaller than the difference to the average, you know you're okay. Did any of that make sense? Barely made sense to me. But the idea is this. So we start at 20, and we start at 100, and we know that the average is 60. And then say we end up at 62. So the idea is we find this change, right? And that change is 42. And we know that that change is accurate even if our measurements, these two, are not accurate, because the error exists in both numbers. So then what we can do is say if we started at 20 and if we went up 42, that puts us above the average and therefore it doesn't work. Can we talk more Tuesday?
Yeah.
We'll talk Tuesday. Go ahead. Where's the 38? Oh, this. You're talking about this number. Okay, sorry, Clara. Keep going. What?
Like, just, you're saying that then you subtract 20 from 58.
Yeah.
38.
Yeah.
But why wouldn't you instead subtract 58 from 60 to get the 2 degrees off that it was from what it was expected?
Because you're going to, and I know that you don't have context for this, you're going to find out that that difference is not meaningful to us yet. The only reason that we're having this conversation at all is because you want to make sure that your data is not broken from the start. So fundamentally, the idea is you know low, also the temperature of the calorimeter, the cold water, you know high, the temperature of your hot water. When you mix them together, that final temperature has got to be less than the average. If it's not, it means that your calorimeter was dumping energy into the hot water, and that can't be.
So these numbers are all just about making sure that
Yeah, these numbers, you'll never write these numbers down. We actually have a name for this. We call them back of napkin calculations. You'll hear that in college. And literally when you're in lab, you'll have scratch paper, and you're always, especially in college, you'll be checking yourself going, wait a minute, did that make sense? And you're just going to be doing quick math, not even stuff you're really recording, just going, was that reasonable? And that's what, and so literally you'll hear them call it in college back of napkin calculations. And that's what this is. Yeah, go ahead.
When we're doing the calibration, are we doing it by 2 points or do we...
No, but the good. So let's look at what we're going to do with this. So guys, here then is what we're going to do. So we are going to dump energy. So let me clean this up. So guys, we're going to start with your calorimeter with we're 20 degree water. You're going to dump in 100 degree water. You're going to make sure that the final temperature is less than the average. Okay? Now this. What are you going to do with that data? Well, guys, remember when we talked about this? We are going to use this data to figure out the heat capacity of the calorimeter. So we're going to figure out if we dump in some amount of energy, how much does the temperature change? Yes? Okay. I think it's this one. Hey, there it is. Okay, so guys, back to our picture. What we are going to do now is find the tip to my pen. New pen. So guys, we are going to calibrate our calorimeter. And so guys, in order to do that, and we'll talk more about this when we go over the lab. Guys, in order to do this, what we're going to do is we're going to do that hot-cold mixing in the calorimeter. Then guys, I want to make sure I write down this equation just the way I gave it to you. Do you have your class notes? How did I give you the heat capacity? It's over here. Never mind. Did I give it to you, solve for heat capacity? Okay, so let's write this down. So we're going to go HC is equal to joules over delta T. And guys, we'll talk more about how we're going to do this when we really get into the lab. But what we're going to do is this. We're going to measure the change in temperature for the calorimeter. Okay? We're going to measure the change in temperature for the calorimeter in all of these messy examples. It would be the difference between the final temperature and the temperature of the cold water, because the cold water goes into the calorimeter first and we let those settle down. So guys, the temperature change is going to be the difference between 20 and 58 in this example. Then guys, we need to know the number of joules that caused that temperature change. And we'll talk more about how we're going to arrive at that once I get the lab in your hands. But then guys, once we're done with that, what that gives us is the heat capacity for the calorimeter. And that will be in joules per Celsius degree. And now guys, here's what we can do. Once we know the heat capacity for the calorimeter, that then allows us to track down all of the energy that's going into the calorimeter as other processes are taking place in there. And so what we'll do when we actually start doing the reactions is we will measure the temperature change of the calorimeter, and by knowing the temperature change of the calorimeter and by knowing the heat capacity, because we found it through calibration, we can then figure out the number of joules of energy absorbed by the calorimeter. Brilliant? Brilliant. So now we've tracked down 2 of our 3 energy absorbers. This is the energy absorption of the calorimeter. This is the energy absorption of the water. What's the other energy leak we've got to be able to quantify? Through the calorimeter into the room. Huh? Guys, this is brilliant. Clean screen. I would encourage you to actually, what does your paper look like? Do you have room? So if you're up here at the top, you just need about this much clear space. And if it's within 2 or 3 lines of your calorimeter, you're fine, but you want to write this down. Guys, here's what we're going to do. We are going to track temperature, no we're not, time versus temperature. Now guys, here's what we're going to do. Don't write this down because it's going to get messy. But remember what we're saying. Let's talk about our calibration process where we have 20-degree water inside the calorimeter and we're dumping in 100-degree water. So guys, before, and don't draw this with me until you see the whole picture. So guys, imagine that we've got a thermometer in this and we're measuring the temperature of the cold water. So as time goes on, let's say this is 20, this is 0, this is 100, and then let's say this is 60. That'll work. All right, so guys, here we go. At time low as we measure the temperature of the water and the calorimeter. Don't write this down yet. It's 20 degrees. And then, guys, when we dump in the hot water, what is going to happen to our temperature reading? It's going to go, ooh, hold on, that's tailing a little bit, and I don't love that. Let me just erase. So, guys, sorry, and, well, be gentle with me. But this is 20 degrees, and then we dump in the hot water, and it goes boom. Does it go up to 60? No. It goes up somewhere in between. You might get a little bit higher spike simply because of, but you're stirring. So guys, we dump in the hot water. We are going to call this time zero. Draw what you can draw this now. Sorry, did that get weird? So this, let me get rid of that line at time zero. But this is time zero. So we hit this spike. But then, guys, this. If we were to allow time to continue on, what's going to happen to our temperature? Is it going to be horizontal? No, it's going to go down. And guys, assuming that 20 is room temperature, in a couple hours, it's going to have gone back down to 20 degrees. Now, guys, understand this is wildly exaggerated. But guys, follow this logic. This is brilliant. Ready? Why does the temperature go down over time? Energy is being lost through the calorimeter. So it's this. But guys, let me ask you a question. This is cool. Does the loss of energy actually begin after the hot water is dumped in? No. It's losing energy all the time. So guys, during this mixing process, as the temperature is going up, it is still losing energy to the room. So what if it didn't lose that energy? And the answer is extrapolation. And guys, I'm not going to touch this to my screen because it's nasty. But guys, if we could take this line and if we could carry it backwards, oh, that's bad, backwards following the slope. So the slope goes like this, like this, like this, like this, maybe like that. That's better. Guys, this is actually what's happening. At time zero, when we dumped in the hot water, had we not lost any energy to the room, the temperature in theory would have spiked to right there. That accounts for the energy that's lost to the room during the entire process. Get it? This then gives us the 2 points for our temperature change for the calorimeter. It is from here, 20, up to here, which represents what the temperature change would have been had energy not leaked out of the calorimeter. That's brilliant. Do you get it? So here's what we're going to do with that. That brings us back here. And guys, this then is, you could draw an arrow to it, but I'll go like this. Constant, constant, constant spike, down, 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 extrapolate, time zero. This is your delta T, and that accounts for the energy lost to the room. Brilliant, right? So guys, questions or thoughts about any of that? Y'all good? Yeah.
How would you calculate all of that? Isn't it just like a general linear slope?
Exactly. And what you're going to find here, let me give you the lab. What you're going to find is that this slope is so insignificant because, frankly, we build pretty good calorimeters. You're going to find that for some of you, the slope, is this zero slope or no slope? This is zero slope. You're going to find that for many of your graphs, it's horizontal. It's zero slope. Yeah. which you know is not true. Should I give you one for Lynn's?
Yeah.
Let's do. What you're going to find is that you know that's not true. It's actually bleeding energy, but it bleeds energy so slowly that over the time that we're doing the lab, it really ends up being, oh yeah, we're not using it. I know. All right, so guys, let's pull all these thoughts together and let's talk about your pre-lab. Okay. Here we go. So guys, looking at this lab, starting on page 319. Hold on. Wait. This is the lack of focus that leads us to trouble. So guys, starting on page 319, notice your reactants, acids and bases. We are talking about neutralization reactions. So the base, the 1 molar sodium hydroxide, is going to be your reactant in both trials. In one, you're going to neutralize a strong acid, HCl, and the other a weak acid, acetic acid. Okay, so moving along. That is actually what our calorimeter is going to look like on 320. Do you see it? But what we're going to do is we're going to introduce a stirrer, and we'll talk more about that. And then, guys, actually our nested cups are a little more significant than those, and you'll see. Okay, now, guys, moving along. One of the things that we did not talk about is this. Join me at the board. I needed to wait for you to see this before we could talk. Talking about this calibration process. Guys, we talked about the idea that when we calibrate our calorimeter, the calorimeter is going to start at the same temperature as the cold water, right? Then we're going to dump in the hot water, and then our final temperature should be below the average. So let's just use some general numbers. So using those numbers, we'll say we started at 20, we threw in 100, and we ended up not at 60, but at 58. So guys, then we need to talk about how we're really going to deal with this. Ready? Because the end game, forgive me, but let me go back. The end game is that we need to find out the heat capacity, right? So in order to find out the heat capacity, we need to know the number of joules that went into the calorimeter, and we need to know how much the temperature changed. That leads us to this. So guys, given the numbers in front of you, what is the temperature change for the calorimeter? 38 degrees. Remember, the calorimeter starts at the same temperature as the cold water. So the calorimeter went up to 58 degrees. So guys, our delta T for the calorimeter would be 38 degrees. Okay? But then, guys, we need to know the number of joules of energy that caused that change. This is the tricky bit. How much energy caused that change? So, guys, watch my hands. Here's the energy of hot water. Here's the energy of cold water. When you mix them together, where does the energy end up? Not temperature, energy. The energy ends up in the middle, right? But it actually doesn't. Watch again. Hot water, cold water, when they come together, they end up a little bit below the average. Why?
Because energy is being lost.
Yeah, energy is being lost into, not the surroundings yet, into the calorimeter. How much energy is being lost into the calorimeter? The difference between the amount of energy lost by the hot and gained by the cold. This is what that looks like. So guys, you're going to do two calculations. You're going to go Q is equal to MC delta T. And that is going to be for the cold water gaining energy. So mass is the mass of the cold water, C is the specific heat of water, and in this case, the delta T would be 38 degrees. Is that okay? Say no if it's not okay. That okay? That will give you the amount of energy gained by the cold water. Then you're going to do it again. Q is equal to MC delta T. M is the mass of the hot water. C is the specific heat of the hot water. Guys, what's delta T? 100 minus 58. That would be 42 degrees. So the temperature change for the cold water is 38 degrees. The temperature change for the hot water is 42 degrees. So guys, if mass and C are the same, this is going to represent more energy than that, right? The hot water's temperature changed more, so it lost more energy than the cold water gained. Where did the energy go? Into the calorimeter. How can you figure out how much energy that was? Subtract. You're going to take the Q for the hot water and the Q for the cold water and subtract, and that's the number that will be the energy change for the calorimeter. So you're going to plug in those joules, which come from subtraction. You're going to plug in delta change in temperature, which is the change in temperature from the cold to the average, to the final reading, and that'll give you H sub C. Did that totally blow your mind? Are you now really glad that I have a calculation page that I'm going to give you? Mm-hmm. Dun, dun, dun. I'll give it to you later. You want it now? Okay. Which is really sad. If this gets you excited. Oh no, you have to write a lot. Sorry, start again.
So if you figure out the heat of the calorimeter,
yeah.
Instead of plugging in the heat of change of 38 degrees and change of 42 degrees of water,
yeah.
you just do the change of 4 degrees of water.
The reason that I mean, in theory, in this case, sort of. So your mass would have to be additive, because now you've got the mass of the whole mess, 100 grams. But the problem is, and the reason that we won't approach it that way, is what if the masses weren't the same, and what if the substances were different? So to do this fairly, we're going to keep them separate. I like how you're thinking, though. Okay. Hold on a second. So now, guys, back to the lab. Guys, yes, please. Do you have the take her the basket? That's hers. Yeah. Okay. So now, guys, continuing on. Looking on page 320. See where we've got at the bottom, equation number 2, heat lost by the cold water, heat lost by the hot water, heat gained by the cold water, and then down below, the heat lost to the calorimeter is the difference between the heat lost by the warm and the heat gained by the cold, and there's your subtraction. Yes? Now flipping over. Now, guys, moving along through the lab, let's now go to the procedure. And look at the bottom of page 322. Clara, this was to your question. Guys, do you see the graph? That's really what this graph is going to look like. Your slope is going to be amazingly shallow. For some of you, it will literally be horizontal, which simply means that your final temperature is the same as the temperature that you actually measured. But guys, notice that this allows us to identify delta T. Got it? Okay. Then guys, looking at the procedure, the first thing you're going to do is you're going to calibrate by finding the heat capacity of the calorimeter. That's where you mix the hot and cold water. Then once you've collected that data, remembering that we need that our final temperature to be below the average, you then go on to B and you use that calorimeter to study the neutralization of a strong acid. Then you go on to part C and you use it to study the neutralization of a weak acid, and then you're all done. Okay? All right, now guys, go to the pre-lab on page 223. You're going to do 1. You're going to do 3, 4, 5, 6. 1, 3, 4, 5, 6. 10. 1, 3, 4, 5, 6, 10. Okay, so guys, this then defines your existence on Friday. Oh, wait a second. Claire. Yeah, you have Friday. But for Lynn's, or did I give you one? Oh, good. Okay. So, guys, let's then talk again about Friday. Chapter 19 summaries. Those don't have to be due on Tuesday. So, as you're prioritizing your time on Friday, guys, highest priority is finishing up the quant lab. That's a gotta do. And then the pre-lab for this lab. Then, if time permits, we are going to do summarizing chapter 19. But guys, don't take that. That's going to be due like next Thursday. You need to go? Go. Okay. So guys, again, first priority, finish quant lab. Second priority, pre-lab, this lab. Those you should get done. You got both periods, right? Then any remaining time can go to summarizing chapter 19 using the same format you used on 5. But that does not have to be due on Tuesday. We can push that back. Let's not do homework over the weekend. It's homecoming. Look at how thoughtful I am. Oh, it's all about the love. You just got homecoming love.